Um, if you remember, we are trying to follow more or less a historical path. So we are pretending that we are sometime before 1974, and we are faced with the problem of describing strongly interacting particles. And we're given the information that there seem to be an infinite number of them. They are massive, and they have what seems to be any kind of spins. Okay. And we talk about Veneziano, that people realize that that these S metrics could come from the interaction of strings. So what we said was that we wanted to describe or to model something like this, where we had our particles coming in, exchanging what seems to be an infinite number of massive particles. And the way we wanted to describe this was by saying that this was really the interaction of some open strings getting together and then breaking apart into two other open strings. So people usually start a string theory course by giving you the Nambu Goto action. So that's the usual way to start the course. The usual path is to start with the Nambu Goto action. And the reason is that people usually start by saying, well, we want to describe strings. So what do we want to do? We have a space-time where we have time and we have some space directions. And we want to describe a string moving here. Well, if we know how to describe a particle moving in a space-time, which is through an action that computes its proper length, okay? Well, the natural thing for a string is to start with an action that computes the area. Okay? And then a standard course will proceed by saying, well, this action is too difficult. We don't know how to quantize it. It's very hard. So let's introduce a trick. The trick was introduced by Polyakov. And then we go from this action to the action where we have the inducement, the X fields and the H, and the metric H on the wall sheet, which is a Polyakov action. Okay? And then the course will proceed by quantizing this action, exactly what we have been doing. Now, I didn't choose to do that because you guys have taken many GR courses, so you're very, very familiar with GR. And therefore, it was more natural. So what we did was to start with studying GR plus scalar fields in any number of dimensions. Well, remember, we also had a cosmological constant. Once again, the reason we did that is that you are all very familiar with that, okay? And we studied the case m equals 1. We found that if you interpret the scalar fields on this 0,1 dimensional field theory, if you interpret the scalar fields as being something that maps this word line into a space-time, then we were describing the motion of a particle in some space-time. Okay? Then we did m equals 2 and realized that what we get is precisely something that describes the motion of a string moving in a space-time. And we landed directly on the Polyakov action, and you guys did the exercise of going and showing that you get the Nambu-Goto action, okay? Now you may ask, why not continue, right? It seems that this path ended up being something interesting. Why don't we go to m equals 3? Maybe we will get a theory of membranes moving in space-time, right? So m equals 1 was particles, m equals 2 was a string moving in space-time. So maybe for m equals 3, we will get membranes.
This is renormalizable.
Sorry?
This is renormalizable.
Yeah, so 2 dimensions, by now you know, is very, very special, right? In 2 dimensions, we have this. The conformal group has an infinite number of generators. There are many, many good things that happen in 2 dimensions that will exactly break down when you go just one higher, okay? So 2 dimensions seems to be like a very special dimension in terms of quantum field theories. So good thing, the string happens to be a 2-dimensional object in space-time. In space, it's a 1-dimensional object moving in time. So it's just a 1 + 1 dimensional quantum field theory. So the reason we don't go to 3 is that we don't know how to do it. Okay? Now, remember, this is what we're doing. Okay? So we're quantizing this string. And where are we going with this? Well, where are we going? And I hope we will get to that today at the end of the lecture, is to say, well, this is what we want to do. We will quantize this action. We will find that, remember, the target is to describe this in how many dimensions? In d equals 4, right? So the goal is to show that this action can be quantized and that the number of scalar fields can actually be 4, right? Because we want this string to move in 4 dimensions. Are we going to succeed? No, we're going to fail miserably, right? Okay. We're going to fail miserably. And moreover, we will find that in addition to these massive states that we wanted, we will also get massless states. So we'll find 2 problems. And those 2 problems will lead us to abandon the idea that we should be interpreting this as a theory of strongly interacting particles, and instead, as people did in 74, interpret our theory as a theory of quantum gravity, or something that could give us a theory of quantum gravity. Okay? Very good. So that's where we are now. We are trying to quantize this, and we still don't know that there are problems. So I don't know why you knew that we were going to fail. So we're now playing with this action, and we're trying to study the quantum theory. Now, given that our target is to describe something like this, maybe we should concentrate on open strings. It's also more convenient for the calculations we're going to do because we don't have to worry about tildes and untildes all the time. Remember that I always mess up which ones are which, and then things get complicated. So let's concentrate on open strings. With Neumann boundary conditions. I hope you did the exercise of finding what the oscillator expansion was. I think if you did it, you probably found something that looks like, here I'm using the momentum already, p mu. I'm identifying alpha 0 with p mu up to some string length. So we get something that looks like this. Okay, so I hope you all did it. So this is our object. Now I want to rewrite it a little bit. I want to write it as follows. No, I'm gonna leave it like that for the moment. Okay. So we proceeded. All we did for the quantization yesterday is also true for the open strings. We just have to concentrate on one set of oscillators, so we don't have to worry about having two sets of infinite number of oscillators. And remember, what we did was to define operators, am, to be 1 over square root of m for m positive. Of course, if m is negative, we will be in trouble with the square root with this definition. So we define this to be true for m positive. And then we say that the adjoint operator is given by this for these guys. Okay? So that's the way we define the operators that would actually look like harmonic oscillators, creation and annihilation operators. Okay? Okay, so we found that these guys satisfy an algebra of operators of this form. And we said, well, this looks very good. Looks like an infinite number of harmonic oscillators, except that we had a problem. And the problem is unitarity. In other words, this is a theory where we can have negative probabilities. So that sounds a little bit strange. And how do we know that we have negative probabilities? Well, because we compute the norm of some state. And the state that we chose was anything that has a zero component here, any of those oscillators in the time direction acting on the vacuum. Of course, we want to create a particle, so we have the creation operator. This guy gave us exactly -1 as its norm. Okay? So any interpretation as probabilities will fail. And we said, well, if there is only one guy, there is no problem, right? But we discovered yesterday that there was an infinite number of negative norm states. So we said that the reason, or hopefully the way to solve the problem, is to remember that we also had to impose constraints. Our theory is not just a theory of those oscillators, but it's a theory of those oscillators with constraints that we had to impose, right? Remember, the constraints were things of the form which we've Fourier represented, okay? And we got these operators. Let's, well, and we also said that, well, these guys, they all look fine. They can go into the quantum theory, except when m is equal to 0, we can have normal ordering problems, okay? We also said yesterday that imposing the constraints at the classical level was setting all the oscillator, or all the Fourier modes of the constraints equal to 0. But now in the quantum theory, we have to impose conditions on the physical Hilbert space, right? And we said that the condition was that this, on any physical state, has to be 0 if m is greater than 0. Okay? So somebody, you could have asked during the lecture, but somebody did after the lecture. So why do we do this and not impose the same thing for all m's, for positive and negative? After all, in the classical theory, we had to set to 0 all generators, right? All of these L's. So the answer to this, so why do we set only the positive ones to be 0? Well, first of all, this is not the whole story. We also say that the negative ones, we realize that they are the adjoints of the positive ones. Okay. Now, the reason we don't do that is that these operators in the quantum theory, as you probably know very well, they satisfy an algebra. Okay. So this was the algebra of Poisson brackets in the classical theory. So in the quantum theory, what do we get? Extra. You told me already. Yes, so you get an extra term, right? That looks something like this, with m times m squared minus 1, something like this, right? Delta m plus n. Is it something like this? Like this. No, it's exactly that. Where this is a central charge. So you should all tell me at once, right? I mean, simultaneously, everybody should tell me what the central charge of our theory is. Remember, the Lagrangian is just the Lagrangian of massless, sorry, it's just the Lagrangian of a number of free bosons, right? How many of free bosons we have? We have d of them. So what should the central charge be? Is what? Is d, yes. Very good. Now, let's pretend that we said, well, okay, in the classical theory, we have all these constraints for all m. Let's pretend that we can actually do it. We can ask the Hilbert space to have 0 for all m's, okay? To be annihilated, any physical state to be annihilated by all the constraints. So if we had that, then we could put this commutation relation and sandwich that with our physical states, right? Clearly, if we impose that this condition is true, this will always be 0. Okay? But let's evaluate that in the case where n is equal to minus m. So we're saying that this is 0 on the one hand, but now using what this is, we're going to find something that looks like 0 here. Not quite, right? Remember, this is L0, so we get phi L0 plus d over 12 m times m squared minus 1 phi phi. Okay? Remember, we said last time that we should allow this to have a normal ordering constant. So this acting on a physical state will not give us 0, but it will give us some a. And we said that a was a number, was just a fixed number. Okay? We don't know what it is yet, but it's just a number. Well, clearly this is impossible to satisfy, right? Because this would imply that a plus d12. Well, of course, I forgot here there is a factor of 2m. for all m. And that would be a contradiction. So remember, we're doing this under the assumption, this is under the assumption for all m, okay? Now let's do it under the correct assumption. Now this is correct. The correct assumption is that this is equal to 0 only for positive m's. So if that's true, we don't get 0 anymore. What we get from here is that one of the two terms vanishes, and the other term, so maybe we can write it explicitly. So there will be a term of the form Lm L minus m phi equal to plus or minus phi L minus m Lm phi. So this one is clearly 0 by our condition, and this one will not be 0, but it will actually be the norm of the state L minus m phi squared. So what we are learning is that if we impose this condition, then we know how to compute the norm of these states, and it's given by this equation here times the norm of this. Assuming that it's normalized, then the norm would exactly be equal to this. Okay. So I hope you all have seen this. I mean, this is something that you probably see in the conformal field theory course. Okay. Sorry, how did I what? Why when I use the correct condition I don't have problems? Well, because what I get is that I don't get 0 from the first term, right? When I sandwich this in between the physical states, I don't get 0. Instead, I get the norm of this state, right? Remember, I'm not imposing that that guy is 0 anymore. And we also know this, right? So the first term there is the norm of that state, right? So what we're learning is that the norm of that state has to be equal to that quantity. Is that clear? Probably it's not clear. Was it too fast? Maybe. Let's go down. So what's the logic? We know that this is true. We want to know whether this is consistent with assuming that the constraints on the quantum theory must be that all LMs must annihilate a physical state for any M. Okay? So in other words, here on this part of the board, we're doing something wrong, but we want to learn why. So we assume it's true. We assume we can do it. Under this assumption, it's clear that this will vanish, right? But if I replace this by the right-hand side of this equation, I get 2 times m times L0, 2 times m times L0, sandwiched between these two guys. But L0, acting on the physical state, can only give me, or all it can do is to give me a constant, which is this normal ordering ambiguity that we are parameterizing by a number, times the norm of the physical state, times this 2 factor 2m, plus the rest. Okay? But we need this to be 0. We find that this is 0 for all m. And therefore, we will have to solve this equation. But we only have 2 variables and an infinite number of equations. So that's a contradiction. Is that clear now?
L's of n, which is n is negative, right? So what are we going to do with it?
No, now what we're doing is that since this is true, right, what is true is that L minus m's annihilate the dual space. So the LMs annihilate the physical states for positive m's, and the L minus m's annihilate the dual physical space, right? The dual Hilbert space.
Right. So what's A? We don't know what's A.
Oh, no, we don't know what A is. A is a number, but it's just one number.
Okay.
It cannot depend on m, right? Because it was computed by the normal order ambiguity in the definition of the quantum operator L0. L0 is just one operator, right? It has just one normal order ambiguity. It cannot depend on m, right? It's just a number. Well, today we will find what that number is. Okay, very good. Now back to our problem. We said that we have an infinite number of gauss somehow, right? Our negative norm states. And we want to find a way of projecting them out of the Hilbert space. Okay. Then we said that we also have an infinite number of constraints to impose. Which are all these constraints. Now, that looks very complicated because these constraints are quadratic in the oscillators, right? These LMs are quadratic. Or if we go back to the original way of writing them in terms of x's, they are quadratic, okay? So how to impose, that would be a very, very messy computation, trying to impose an infinite number of constraints which are quadratic. So we have to find a way of simplifying this, or a trick to simplify this. So we want to find a way of linearizing. Okay, so that's what we're going to do. It's not going to look like that at the beginning, but that's what we're going to achieve. Okay, so I'm just warning you that what we're going to do now, the whole purpose of what we're going to do is to linearize the constraints and solve them. Okay, so that goes, or that construction is actually something that people use very much in quantum field theory already, or that it was well known in quantum field theory. And it's called the Lycon quantization. Yes. Sorry? Oh, they came from the very strange and surprising fact that our metric has a Minkowski. It actually has a negative term in the one of the entries is negative. That we live in Minkowski space. That's the reason, right? So let's see. Where did we do that? Oh, here. Right. Take this oscillator. Take this physical state. The zero component, right? So this is crucial. The most important thing in this formula is this zero here. And the reason is that when you compute this, what you get is this guy But remember, how do we usually compute this? Well, we use the commutation relation so that we send this guy, we put this guy next to the vacuum so that it will give us 0. Remember, the vacuum is defined so that that's the definition of the vacuum. So when we use the commutation relation with 0, 0 for the space-time indices, well, first of all, this thing is equal to the commutator. And here is a crucial point. This thing ends up being equal to eta 0, 0, which so happens to be minus 1. Okay? In the gauge fix, yeah. So no, we are not doing. Oh, in which gauge fixing? What are you talking about? Quantum field theory or in quantum field theory? Yeah, this is very. I mean, that's precisely what you do in quantum field theory. You then do the Lycon gauge in order to quantize your theory, only having the physical degrees of freedom. That's what we're going to do. So that's why I said that. Well, the trick was already understood in quantum field theory. So why not use it? Okay, so let's do the Lycon quantization. So what's the idea? Well, first of all, we have to go to Lycon coordinates in space-time. Okay. So we started out with our space-time coordinates, or our scalar fields on the world sheet. Okay. And in terms of these coordinates, we had our metric, which was -1, 1, 1. Okay, the diagonal, the matrix whose diagonal is -1, and the rest are +1s. Now we want to go to Lycon coordinates, where we define two coordinates, x plus and minus, by 1 over the square root of 2, x0 plus minus x1. Okay. The square root of 2 is just a convention, but it's so that the metric will look nice. So when we do this, and whenever you see a vector now written in the formulas with an index mu, we should really be thinking about x plus, x minus. Sorry. Actually, the standard convention is to write this as d minus 1. Okay. So you will have x plus, x minus, x1, x2, all the way to xd minus 2. Okay. Now, in terms of this, the metric looks like the identity d minus 2, d minus 2 times 0, minus 1, minus 1, 0. Okay? So that means that whenever you see, say, you have a vector u, so here I'm going to introduce some notation just to say that whenever you see an index I, it only goes from 1 to d minus 2. So people like to call by I and j the indices in the transverse direction, okay, to the Lycon that you're choosing. So if you have a vector, so this is a vector, and you have another vector v, sorry, you have another vector v, then the inner product of u dot v, just, well, it's trivial. I gave you what the metric looks like, but let's write it explicitly: v minus u plus v minus minus u minus v plus plus, if you wish, the transverse directions. You just do the usual dot product for them. Okay. So this is going to be useful for us. Okay. Now let's go back to our open stream formula here and realize the following. Well, first of all, now the negative norm states will be produced by what kind of oscillators? Before they were produced by the alpha zero oscillators, right? So the negative norm states here will be produced by what kind of oscillators? Yeah, so it seems that we made the problem worse, right? Now we actually have two sets of oscillators. Every time we see an alpha plus and an alpha minus, we're going to be in trouble. Well, sometimes things have to get more complicated before they simplify. So that seems to be one of the cases, okay? Very good. So we have to pay close attention to, say, x plus and x minus. So those will be the oscillators that will give us trouble, right? Alpha plus and alpha minus are now the bad guys. So let's look at this guy. And let me write it like this. Well, if I pull one out, so this thing would look like. So remember, P mu is also a vector, so it also has a plus component. It goes with this plus component. Well, I really didn't do anything special, right? I just rewrote this formula. Sorry? Small, yes, thank you. Yes, very good. Okay, so now we have this formula.
Question.
Yes.
In this formula, in the second term to the right, on the right-hand side, is it LS or LS?
Where here?
No, in the previous line.
Yes.
Yeah. Is it square?
Yeah, I think so, right? Because P has dimensions. It was LS without the square when it was alpha zero, right? Okay, so you see we have this infinite number of bad oscillators here. If we could just make a change of variables and get rid of this tau by declaring that this is a new tau variable, wouldn't that be great? Well, if we want to do something like that, we could, of course, try it and do it, but then our action under that change of variables would be a mess, or that's what you would think. So remember, our action is something that looks like this. In world sheet-like coordinates, it looks like well, let me write it explicitly. Mu, right? Well, but once again, from your CFT course, you should realize that this action has an infinite number of symmetries. What can I do to sigma plus that will leave this action invariant? Well, imagine that I make a change of variables, and I define sigma plus tilde. Well, this is really the secret reason why we're not doing the closed stream, because then the tildes would get completely confused all over the place. This tilde only means a new variable. Okay, I could call it prime, but then prime means derivative with respect to sigma. So this tilde here only means a new variable, okay? So if I make this new variable just a function of the old one, not of sigma minus. In principle, I could try both, right? But if this guy only depends on sigma plus, then this action is invariant. Likewise, I could do the same thing with sigma minus. Any function of sigma minus will do. Sorry? Oh, yeah, thank you. Yes, very good. So what kind of transformations are these transformations? These are conformal transformations, right? These are conformal field theory. These are conformal transformations. And the generators are precisely the Virasoro generators. And that's the reason why we have all this algebra sitting there, okay? But for the time being, what is important is that these are symmetries of this action, okay? At least classically, they are symmetries of this action. So let's rewrite this in terms of tau and sigma. So what is this? This is tau tilde plus sigma tilde is equal to f plus sigma plus. And now this guy is tau minus sigma tilde is equal to f minus sigma minus. Now, if we add up these two equations, we find that tau tilde is equal to a half f sigma plus minus f sigma minus. Okay? Isn't that amusing? Tau tilde as a function of sigma plus and sigma minus actually looks like an oscillator. It looks like a string, or at least looks like the coordinate of a string, because it only depends on sigma plus, any function of sigma plus, and any function of sigma minus. In other words, our new coordinate, or we are free to choose any coordinate tau tilde such that it satisfies this equation. So any such change of variables, any new tau tilde you want to define such that it satisfies the free wave equation is allowed. It's a symmetry of our theory. Well, now our wish came true, right? This thing here, this object, satisfies the wave equation, right? This whole thing satisfies the wave equation. And therefore, nobody stops us from making a change of variables so that this whole thing is tau tilde. So at least we didn't make the problem worse. Remember, before we only had the alpha 0 oscillators as the problem. Now we had alpha plus and alpha minus. And by realizing that we had this symmetry, we can get rid of all the alpha plus oscillators in terms of the new variable. And we're left with only the alpha minus oscillators as our problem. So now our new coordinates better do something important, because otherwise we have been wasting almost an hour on this. And here comes the part that I promised. The new variables, or the new coordinate system, will do the job of linearizing the constraints. So let's look at the constraints. Let's choose this form of the constraint, right? Remember, we have many ways of writing the constraints. Let's just choose this one and see what happens. Explicitly, remember, this is, okay. I don't have to do it like that because I already did it over there. Let's call this vector let's say that x dot mu is our vector u, and x prime mu is our vector v. And let's use our formula here. Let's use the formula there, okay, in order to write the constraint. So let's write the constraint. Then it's minus x dot plus, so try to pay attention because the chances I'm going to get some index incorrect, or a prime or a dot, are high, minus x dot minus x prime plus x dot x prime equal to 0. Now, this is at the classical level, right? We're imposing this as a classical equation. In the quantum operators, these guys will have to annihilate then the physical states. But let's keep this computation as a classical computation first and see how the constraint simplifies. Now you see the magic, right? I hope. Let's look at our new x plus. Let's write it more explicitly here. Our new x plus in our magic coordinates is x plus plus ls squared p plus tau tilde. Now, let's look at this guy here. X plus dot. The dot means derivative with respect to tau tilde. When we take the derivative, this gives ls squared p plus times x prime minus now we have x prime plus, but x prime means derivative with respect to sigma. And here comes the magic. Derivative with respect to sigma. Which sigma? X plus doesn't depend on sigma. So you get 0. Big 0. Now you see the magic, right? This is the linearization we got. Before we had something quadratic, and now we got just a number times x minus prime, 0 here, and we get everything in terms of oscillators we like, right? So this means that x prime minus is equal to 1 over the stream p minus, or p plus, sorry, the sum over I from 1 to d minus 2, x dot I, x prime I. Okay? Very good. Now we just go back to our formula on the top, right, for x minus, and we compute x minus prime from the formula on top of this value at the top, okay? And what do we get? Well, it's the derivative with respect to sigma. So we get something that looks like ls sum over m different from 0, alpha m mu e to the minus I m sig tau tilde cosine of m sigma. Of course, the most important thing, I got it wrong. The whole thing was to say that this guy appears here, right? So this is our set of bad guys now. Sorry? Oh, yes, 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 of course. Thank you. Yeah, that stays. At least I got that the m went away, right? No, I got that one right. Come on. There is a 1 over m in there. And a minus sign. See, you're witnessing a miracle happening. The whole thing is linearized. And then you're worried about minus signs. Of course, well, the cosine, okay, that one was important, yes. That one is really important. Now you see, you plug this guy here, Now you plug what these guys are from the same formula. This would be a bunch of products of oscillators. And from here, you get a linear equation. Well, it's a Fourier decomposition. And now it's trivial to find what these guys are. Well, if you want to find Lm or Ln, right, what you have to do is to take all that formula, all this formula, and integrate from 0 to pi the sigma cosine n sigma times the whole formula. That will project out everything else but this oscillator on this side. And on this side, it will give you whatever it gives you. Do you agree with that? I want, this is that object, but I want to read this guy from the formula. Well, first of all, this doesn't depend, these guys don't depend on tau, so we can set tau tilde to 0 if we want from the beginning. Yes? Why what? Okay. All right. So you do this, and then you find what this guy is in terms of the oscillators we like. Okay? Yes. That I can write what?
That you can write tau tilde everywhere for the rest of the components? Because you
Why
define
not? I did it from the very beginning. What I'm imagining is that from the very beginning, I made a change of coordinates. And then this is what happens, right? I mean, that's why it's important that this is a symmetry of the action. Otherwise, everything would just, if we do something that was not a symmetry of the action, then all the work that we had done would be completely spoiled, because then the action would look very different, and everything would be different. Okay, so this formula is so important that maybe we should write it here. After all, that was the purpose. So what we get is a sum. So I want to get this one right without. So since we're not deriving it, do we want to write the other sum? Yeah, it's probably important. Okay, so this is what you would get if you did this computation to extract what this guy is in terms of the oscillators with only indices in the transverse directions. Okay, but we're interested in this in the quantum theory, right? So in the quantum theory, if you did that, everything will go through, except that, of course, for n equals to 0. Yes. My summation is over m. Yes, very good. Yes. You're so picky. Of course, you knew what the right thing was. Not even copying it from the paper. Okay, so in the quantum theory, what happens is that, well, we want to put normal order in here, right? But when we have alpha 0, we have to remember that we have to compensate because L0 should not annihilate the Hilbert space. So we have to compensate by our normal order ambiguity, okay, that will appear here. Very good. So now we got rid of all the troublesome oscillators. So alpha plus and alpha minus oscillators are not there anymore. So our physical Hilbert space is only constructed from the transverse oscillators. So that seems like a victory. It seems that we're done. Well, not quite. So let's write our physical Hilbert space. So we have states of the form AI1, M1 dagger, AI2, M2 dagger, AML, IL dagger acting on the vacuum. At our physical states, they all have positive norm. Everybody's happy, except that there is this index I sitting all over the place. And we really would like to have a mu index, not an I index. This I index only goes from 1 to 24, to D minus 2, sorry. It's just that by this time, we should have already got it. Okay, so these indices go from 1 to D minus 2. Okay, so that's a problem, because it means that Lorentz, so unitarity, we got it to work. That's very good. But we might have spoiled something else. We might have spoiled Lorentz invariant. Okay. So how could that have happened? If everything we did seems to be completely fine, okay? Well, there was one assumption that we made at some point, which might not be correct in the quantum theory. And the assumption was that this action was invariant under these transformations. That's true classically, but in the quantum theory, we might get an anomaly, okay? If the anomaly is not there, then everything we did is fine, and the theory will be Lorentz invariant. But if there is an anomaly that breaks this symmetry, then our theory will not be Lorentz invariant, because the steps we use to get there are not true. So to connect the original theory, which is Lorentz invariant, to the theory that we got here, we had to assume that everything we did was true in the quantum theory. Okay? So, well, but why not be optimistic and say that we just have to check? Okay, how do we check? Well, let's start to compute. Well, we have our theory, we have our Hilbert space, right? So let's start by computing the spectrum of the theory. How do we compute the spectrum? Well, actually, the key to computing the spectrum is that formula over there, precisely. The reason is that we can now rewrite this formula by noting that for n equals 0, alpha 0 minus is proportional to p minus, right? That we know. Now, if we multiply, we pass this p plus to the other side, we will get a formula that looks like p plus p minus, okay? And on the other side, if we take the m equals to 0 factors, okay, the m equals to 0 term, so let's split the sum as we did before, yesterday or the day before yesterday. Let's take the m equals to 0 piece. The m equals to 0 piece will give us a sum over pi dot pi from I1 to D minus 2, right? Those will be the m equals to 0 terms in this sum. The other piece, since it's normal order, we can very happily combine them into a single thing for m from 1 to infinity only. The sum, you probably don't see here, right? The sum from I1 to D minus 2 of alpha I m minus, so we have minus m alpha I m, okay, with our, well, in fact, in this case, we just get A, right? Well, I'm probably missing, there is a factor of 2, right? So the factor of 2, I can put it here. And there will be some alpha prime that I'm also missing, which I'm not going to worry about. So when I move this guy to this side, what do I get? If I move these things to this side, I get 2 times P plus times P minus the sum of Pi dot Pi. That's P squared, right? So that would be, if I now put these guys on this side, this thing, if you work out all the factors, you will get P squared, or minus P squared, and therefore we will get alpha prime times the mass of the object squared. Okay, so that's the formula we want to use. In order to compute the spectrum. Okay, so we're going to compute the spectrum by saying that we want to know what the mass of an object is. All we have to do is to apply this operator, where n is defined to be the sum from m equals to 1 to infinity, and the sum from I1 to D minus 2. Now, these alpha guys are not very nice, right? Yes? Yeah, so the 2, there was a half. So the half goes away with that 2, right? We had a double sum. No, only for a piece of it. I mean, yeah. So what I mean is the following. Let's see, go down. So you have something like this, right? So this will end up being, after you work out all the factors correctly, this thing is 1/2 of P squared, right? And the half was here, but now we double the sum, and we cancel the half. And now if you work out all the factors correctly with the definitions I gave you before of what L string is in terms of alpha prime, there is a factor of 2, right? Then you will find precisely this formula, okay? Okay, so what I was saying was that the alphas are not the nicest operators, right? Because we are acting on the Hilbert space to create particles with the A's, not with the alphas, right? So there is a normalization. So if we compensate for the normalization going from the alphas, remember the alphas, to go to the A's, we have to pay a price of a square root of m, okay? And then we will get an m. And this is for m positive, for m negative, we can, if m is negative, we can call it minus m, and this will be m. So for m, for this thing negative, let's call it minus m. This will be the relation. So we have two such factors. We get m from here. We get I dagger AMI. So that's our number operator. Note that it's slightly different from the usual ones because we have this factor of m here. Okay? Very good. So now we are ready to compute the spectrum. Well, the usual way to compute the spectrum is to go level by level. So we start with the level 0. We want to list all possible states with number operator eigenvalue equal to 0. What are the possible states with number operator eigenvalue equal to 0? The vacuum, yes. States where we don't act with any oscillators, with any creation operators, right? So we want to find the mass of that state. So we apply this operator on the vacuum, and we get minus A times the vacuum. And therefore, the mass of the vacuum is minus A. The mass square. So if A happens to be, A could be negative. So don't panic yet, right? A could be negative, no problem. But if A happens to be positive, then we got a tachyon, okay? Well, let's keep going. N equals 1. Well, in order to get n equals 1, right, given that we have this m here, the only choice we have is to have something like this. These are the only possible operators that will give us n equals 1. How many of them do we have? We have d minus 2 states, 1 per value of I. And what is the mass of this thing? Well, we applied our operator to this, and we get 1 minus A. Let's give it a name. Okay, it's the n equals 1 guy, and there is an index I because, well, there is an index I here. Okay, very good. So the mass of this thing is, or the mass of these guys is 1 minus A. Now, we say, well, very good. So we have d minus 2 states, okay, in this sector. Now, is there any representation of the Lorentz group, of the Poincaré group, right? The original Poincaré group has as a Lorentz group SO1, d minus 1, right? This thing looks like a vector, right? It only has one index, but it only has d minus 2 degrees of freedom. Is there any representation, you know, of SO1, d minus 1 that has only d minus 2 degrees of freedom and looks like a vector? What should that be? It should be a massless representation, right? That's the only possibility. So it's a massless representation. Well, if it's a massless representation, then, and we want to keep Lorentz invariance, so we already see that Lorentz invariance will not work unless we set this to 0. So Lorentz invariance implies that this has to be 0, because our friend here can only be a vector, a massless vector. And the reason is that it forms a vector of SO d minus 2, which is a little group of massless particles for SO1, d minus 1. So we need this equal to 0, and therefore Lorentz invariance implies that A has to be equal to 1. Now you can panic, because then this thing becomes a tachyon. Okay? Very good. I think we only need 3 more minutes to finish what I want to say today. Oh. Okay. So how about n equals 2? Well, maybe I'll leave n equals 2 as homework. Well, as an exercise, okay? But let me tell you what the states are. Well, you can also figure that out, right? In order to have number operator eigenvalue 2, we can only have 2i dagger acting on the vacuum, or ai minus 1 dagger, a minus 1 j dagger acting on the vacuum. So these guys, we have 24 of them, and these guys, we have 24 times 25 over 2 of them. Sorry? You see, that's why we have to get to it. Yeah, we don't have D. D minus D minus 2. This would be D minus 2 times D minus 1 over 2. And your exercise is, well, first of all, now we know what the mass is, right? These guys, A is equal to 1. Therefore, these guys are massive. Yes? Oh, because we need number operator 2, right? So with m equals to 1, so this guy will pass twice through this guy, so it counts the number of guys we have. So it will give us eigenvalue 2. Oh, that's what you're saying. Yeah. Sorry. Yeah, very good. It's plus 1. Now, why did I write minus 1? What? Yeah. You see, I'm writing 26 all the time or minus 1 all the time. The reason is that people usually don't write what I'm writing here because, yeah, so you can get lazy and don't want to write this adjoint all the time. So sometimes people write this thing. Most people don't like to write this like this, and they simply write this. So you see that in my mind, I'm using what I usually use with what I want to use because I want to stress that these are creation operators, right? So you will see people writing I minus 2i acting on the vacuum and a minus 1i. You see, everything has a logical explanation, even the types. Okay, so your job is to find out how these guys can reassemble themselves into what? Into a representation of what group? These guys are massive. So find out how come that these two guys can reassemble into a representation of SOD minus 1. If we don't succeed, then we are in trouble, right? Now, but already this told us that there is a problem, that we have to check the spectrum and we have to check everything, right? Because there is a quantum anomaly in general. But instead of doing this for all the states and painfully doing that all the time, why don't we just go ahead and check the Lorentz algebra? That the Lorentz algebra is satisfied by the quantum operators, right? Well, too bad we don't have time to actually go through the whole commutators and so on. So you will have to do it as an exercise. You probably did in the tutorial, you checked that this thing was given by this. Right? The generators of the Lorentz algebra are given by this. Now, in terms of oscillators, we plug what the oscillators are. So these are just the center of mass positions and the momentum of the string. But now we get this contribution from an infinite number of oscillators. Okay. And now we want to check that these operators satisfy the Lorentz algebra. As I said, we're not going to do it. So the claim is that all these commutators, as you might remember, the Lorentz algebra has a structure like this. The claim is that all these commutators work out perfectly, except for a single set where you take mu to be, the index mu to be minus, the index nu to be a transverse direction. You take the index rho to be minus, and you take the index sigma to be a transverse direction, j. Okay? Now, Lorentz tells us that this commutator has to vanish. Okay? Now you go ahead and plug in this formula and use the commutation relations for the operators alpha, and this is what you find. You don't get 0. In fact, you get an infinite number of contributions here. With some coefficients. So that looks very, very bad. And indeed it is. But now it so happens that if A is equal to 1, which we know will help us in trying to get Lorentz invariance, then these coefficients, well, it's funny, right? Because we only have, what do we have at our disposal? The only variable that we have is the number of scalar fields. So we only have one number, which is the d, and we have an infinite number of coefficients to set to 0. But it so happens that when A is equal to 1, we get something that looks like this. Binary. So we recover Lorentz invariance. Only for A equals 1 and B equals to 26. Note that this is remarkable in the sense that, first of all, there are two miracles. One is that all these guys can actually be killed, that they have a common factor. And second, that the common factor gives us a d, which is an integer. All right? Not only an integer, it's a positive integer, greater than 4. If it had been less than 4, we would also have been in trouble, right? So it's not only that it's an integer. That already is surprising. Even a rational number could have been something else. And it's positive, and it's greater than 4. greater or equal than 4. Okay? Well, so I think this is a good time to stop, but remember, so this, from the point of view of our original goal, was a disaster, right? First of all, we found a massless state, right? We found a massless vector, which is not that bad, right? Remember, there was a photon already there. At the time, we knew that there had to be a photon. So that would be the photon if we wanted. But we got this 26 here. So we got these two problems, and on top of that, QCD came around, and it was proven that the behavior for in deep and elastic scattering precisely agrees with asymptotic freedom, and everything was in bad shape for the string theory as a theory of strong interactions, okay? So I guess we'll continue on Tuesday, right? I think Monday is a holiday. Okay, very good. That's why we went over time today. So that